Welcome to This Explainer. If you've ever just wondered how a signal gets from point A to point B without a single wire in sight, you are in exactly the right place. We're going to break down the core concepts from Unit 2 of wireless communications, really focusing on the essential stuff you'll need to master these invisible connections that, let's be honest, power our entire world.
You know, this really paints the perfect picture of what it means to be a telecom professional. It's not just about one piece of gear or one technology. It's the whole ecosystem. It's everything from the deep science of invisible waves to the hands-on skills you need for maintenance. And at the heart of it all is one single goal: mastering the connection.
So we're going to hit 5 key areas today. Think of these as the fundamental building blocks for any wireless system. We'll start with the actual path the signal takes, then move to the hardware that sends and receives it, scale that up to a global level, and then finally, we'll look at how we measure and verify that the whole thing is working perfectly. Sound good? Let's get started.
First up, we have got to understand the path a signal actually takes. You might just assume it's a perfectly straight laser beam, but the reality is way more interesting and, honestly, it has a huge impact on your signal quality. Let's talk about the signal's invisible highway.
So, you set up 2 antennas. You can see one from the other. You've got a clear line of sight. That's a perfect connection, right? Well, not quite. You might think so, but there's this crucial invisible factor at play that can literally make or break your entire link.
And that invisible factor? It's called the Fresnel Zone. Just picture this, an elliptical, kind of football-shaped region that surrounds that direct line-of-sight path. For a really strong, stable signal, this whole area has to be kept clear. It's just like needing all lanes of a highway clear for traffic to flow.
Yeah, obstructions are the absolute enemy of a clean signal. And it's not just about a tree directly blocking the path. Even an object that just barely scrapes the edge of this invisible zone can cause radio waves to bend. The technical term is diffract. This diffraction creates these little secondary waves that arrive out of sync with your main signal, and that causes interference that weakens the whole connection and tanks your speed. That's why this rule of thumb is so critical. You have got to keep at least 60% of that first Fresnel zone totally clear.
And look, this isn't just some abstract idea. It's quantifiable physics. Check out the numbers for a standard 2.4 gigahertz link, something like Wi-Fi, spanning 3 kilometers. The Fresnel zone's radius, right in the middle, is almost 10 meters. We're talking about a space as wide as a 3-story building that you need to account for. This is exactly how engineers go from theory to practice, planning antenna heights to make sure that invisible highway stays wide open. So, once we've established a nice, clear path for our signal, what's next? Well, the next logical step is the hardware that actually sends and receives it. And that brings us to antenna systems, the gateways of all communication.
Antennas are those absolutely crucial gateways that turn electrical signals into radio waves, and they are definitely not one size fits all. That simple dipole on your home router, it's designed to spray a signal out in all directions. But then you have a massive parabolic dish, which does the exact opposite. It focuses all its energy into one super narrow beam for long-distance satellite links. And an antenna array on a cell tower? That's a super sophisticated system that can actually shape and steer signals to serve tons of users at once. Choosing the right antenna is everything.
Okay, now let's scale things way up. We've gone from a point-to-point link on the ground to building entire global communication networks that use satellites orbiting high above the Earth.
This table does a great job breaking down the 3 main types of satellite orbits, and it shows a really fundamental trade-off. Just look at the direct link between altitude and latency. Geostationary, or GEO, satellites are in a crazy high orbit, which makes them look like they're stationary from Earth, which is perfect for TV broadcasting. But that incredible distance means a significant signal delay, and that delay is called latency. So here's the bottom line. Latency is king for anything interactive. Just like this slide lays out, low Earth orbit, or LEO satellites are way closer to us. This dramatically cuts down the signal's round-trip travel time, making them perfect for things like fast broadband internet, video calls, and especially online gaming. A geosatellite signal has to travel so far that the delay, that latency, makes those real-time applications pretty much unusable.
Okay, so we've got a clear path. We've got the right antennas. We've got a signal flying through the air, or even bouncing off a satellite. But how do we know the system is working efficiently? How do we grade it? This brings us to a really key performance metric, VSWR.
VSWR, yeah, I know, it's a mouthful. It stands for Voltage Standing Wave Ratio. But the name, honestly, is less important than the concept. Think of it as a report card for your system's efficiency.
It simply measures how much of your power is successfully transmitted out by the antenna versus how much of it gets reflected back down the cable toward you. In a perfect world, all the power goes out and absolutely nothing comes back.
Oh, this garden hose analogy is perfect. It's the best way to think about it. A high VSWR is literally like a nasty kink in that hose. The signal just can't flow out smoothly, and that reflected power, it isn't just wasted energy. It can actually heat up and damage the really sensitive components in your transmitter. And that kink is caused by an impedance mismatch, things like a bad cable, a faulty connector, or just the wrong antenna for the job. The goal is always a perfect 1-to-1 ratio. That means every single bit of power is getting out into the world.
So, to measure things like VSW and diagnose these kinds of invisible problems, you can't just guess. Professionals rely on a specialized toolkit. These instruments are basically our eyes, letting us see the signals we're working with.
Let's zoom in on two of the most essential tools in any pro's kit. First, the oscilloscope. This thing acts like a high-speed camera for electricity, letting us see the exact shape of the signal's waveform. It's how we spot things like distortion or noise. Then, when you're out in the field, you'd use a tool like a field strength meter. This measures the signal's raw power at a specific location, telling us flat out if our connection is strong enough. So together, they give us the complete picture of a signal's health, its shape, and its strength.
And at the end of the day, using these instruments correctly is really what separates an amateur from a professional. You can't just guess that things are okay. You have to measure, you have to verify, and you have to document. Proper use of this toolkit is absolutely non-negotiable for installation, troubleshooting, and just maintaining a reliable communication system.
All right, let's bring it all home. We're going to recap the 5 key concepts that are not only crucial for your test, but for having a successful career in telecommunications.
And here they are, your cheat sheet. Remember, the Fresnel Zone is the signal's invisible highway. The antennas? They're the on-ramps and off-ramps. The satellites are the global road system, with different orbits for different speeds. VSWR is your system's efficiency gauge, like the fuel economy. And your instruments? That's your dashboard, telling you exactly how everything is performing.
So, before we finish, here's one last thought to chew on. How do all 5 of these concepts apply right where you are right now? Seriously, think about the Wi-Fi signal in your home. There is a Fresnel zone between your router and your laptop that can be blocked by a chair or even just a person walking by. There are tiny monopole or dipole antennas in both devices. And the VSWR of those little antennas really matters for performance. It's all right there, just in miniature. Understanding these big concepts is the key to mastering any wireless connection.